Hello, I'm Roman. Welcome back to the series of the videos of building the convolutional neural networks from scratch. And in the previous two videos, we actually take a tour into, what is the convolution itself. And in the second one, we've been talking into the backpropagation, so we would understand how to implement the forward pass and the backward pass. And the next thing, we're actually going to build first the convolutional layer. But before we can do, what we actually need is we need the convolution operation itself. Because if you take a look at the example of the Python implementation, if you take a look at for example, the forward pass or the backward pass, we can see that there is a correlate to D. They most of the time use this operation from sci-fi Python package. But when I tried to find, I'm using the Golang as the bare bone to work with the matrix multiplications, and all of the, for example, the dense layers and other stuff were built on top of the Golang. And the Golang is, I think, a very good wrapper around BLAS implementation for working with the matrices and with the vectors, with some additional stuff and a nice Golang API. So what we're going to do, we need, in order to go to the building a convolutional layer, we actually need to have a convolution operation. And this is what we're going to do today. If we take a look at the first article we used in the first video, we can see that there is an example. Well, I'm not sure if it was in this one or in another one, but we can see it here. So we need to build a convolution that, okay, the padding 0. So for the forward pass, we actually need a convolution that is called, what is it called? Valid, this one. And there is another one, we can see it in the full. And if we take, if we search for this one, I'm not sure if I have NumPy. No, I don't have the NumPy documents. Okay, so NumPy, this one. Oh, it's not the NumPy, it's Giphy. So this is the cross-correlate. It's actually not a convolution, it's a cross-correlation operation, and the convolution is another form of the cross-correlation. So we're going to build the correlate to D operation at first, because for the forward pass we need a valid, and the valid is this one that does not rely on the 0 padding in valid mode. What is the difference? Where is this one? So the valid mode is this one with 0 padding, and the full is with some padding, right? We will need padding for the backward pass, because for one of the derivatives that we need to calculate, we'll need to use the full cross correlation. But today we're going to build this first one. So this is the formula that in general used to calculate the output size of the convolution. So we have the input size, which is the input size. I've done scrolling some time ago. Okay, so we have the input size, which is the input size of the input data, plus 2 multiplied by the padding, which we're not using at first, minus kernel size divided by the stride, and plus 1. Actually, not sure if we're going to use. Okay, let's iterate of the stride. We've discussed that in the convolution, a kernel moves through the pixel of an image, but we haven't talked about the different ways in which it can do. Start refers to the number of the pixels by which a kernel moves across the input image. Okay. The example we saw before had a stride of 1, but this can change. Okay, so this is actually, with the straight 1, we have 1, 1, 1. With the straight 2, I think we'll jump for 2 pixels here. This is why it makes it smaller. Let's start from the smallest one. I will ignore the padding and the stride. So my formula will be input size minus kernel size plus 1. This is what we're going to build. And for me, I will need to have two things. The first one is, well, I'm not sure where to build it. I need to have an operation that is actual cross-correlate function that takes the data from the input the same size as the kernel and does the multiplications and returns the result. So we'll start from this one. Okay, so let me find some example. Okay. I'm still not sure what should be the type of the data for this one. Should it be the just two-dimensional, or like should it be just the floats? The float slice, or I can build it with the matdense. I'm not sure yet how I will write the final. Okay, so we have the input slice. Okay, let's start with the float. Okay, so moves float 64, and then we have the kernel. Same. And what we return the, again, float 64, right? So what we should do, first I need to assert that the size of, I'm not sure if I need to return an error or I can just panic. Maybe just for the simplicity of the code, I will panic. So if okay, mul performs element-wise multiplication between DST and S and stores value in the DSD. So what I can do, I can actually do this. I can do input, and I can have the kernel. Then I can have the sum, which is the floats. I think we have the sum. Sum returns the sum of the elements of the slice, and we take the input. By the way, we don't actually need it. All right. The result of the correlate to D is just a number, right? Let me check. So in order to do this, they should be the same size, right? Or yeah. Yeah, so this is the slice. of it, and this is the kernel, and this is the output. So what should I do? I mean, I could, let's write a test. So it's actually test correlates v, and we need to have an example. Let's take this one. So we have 0, 1, 3, 4, right? And in okay, let's take a look. Okay, one. Okay, 0, 1, 3, 4, 0, 1, 2, 3. Okay, just incorrect the data. Okay, that works. Interesting, what will happen now? Will it fail? Okay, so it actually fails. But how I can... Okay, yeah, I guess the only way to properly cover it with the test, I mean for the test scenario when there is an error, it's just, well, return an error, as what usually happens in the Go. So instead, that should be like this, right? Right. So here that will be oh wait, no, errors new. I'm still getting used to the new keyboard. My friend gave me the mechanical keyboard, and yeah, I'm missing keys quite often. So will it? Wait. How it was? Search diagnostic. Okay, there should be no error. Okay. Tests. So this one should return error. So I'm not interested in the result. Error, and if error for some reason is not equal to new, then we fail. Okay, so how we can test it? Okay. And do this. Okay, so now we have all of the tests. Wait. Okay, so the correlate to D. Well, I guess it's correlate. I think it should be called valid, right? Test correlate to D valid, and here, because I will need to implement the full correlation, which is a little bit different, or maybe like in the end it will be one function that does all of the things. Well, maybe actually the naming is not that correct, because what I actually need is the correlate to the function that operates on the two arrays. So this is actually not. Wait, how it looks like? Where is this one? Okay, so for the range I in the number of the filters calculating, there is output shape. So for the range, so there is number of the outputs. We have the correlation between the input data and the filter, and we have the mode. Okay, so it's actually, this one is not the correlate between the input and the output. I would say this is the correlates to the operation, right? Correlate to the operation. Okay, I like this one more. But right now we actually need to build the correlate to the valids. I think that should be. But here instead it will return okay, so this one will be actually the dense, probably. There is a good question how I will define the kernels, because I can. Okay, let's go with the dense right now too, and that will return the dense again. Right? So then the first thing, what we actually need to do, allocate output. Okay, so we have the input and we're going to implement the valid one. So the valid one is this one. And the first thing we need to actually calculate the result. We assume that the matrix is... That's actually interesting. So we assume that they always same size, or I mean they always square. Okay, so they always square. So the output size, input size. Well, I guess we can do them rectangle, but probably no one actually does it. Okay, so this is what we're going to do. So they will both square, so we need to take we're taking the n, which is this one, right? Input in. Then we're taking the m from the kernel. So we have the number of the rows, and that is usually m minus m plus 1 is 1. And we don't have any data, so that should give me something. Okay. Okay, so and that's the result, right? Then the next thing, we actually need to iterate over the output, and we are going to calculate the output. So right now it will look like this. So for I in a range, no. Okay, I think that should be separated. So I equals to 0 or less than s, and we have the same for this one. Okay, so then we are going to calculate the value, right? Okay, so now it's 0. Then we have the output set I, j, and the value. Okay, for the kernel, we actually can... I mean, for the kernel, it's pretty simple, but the interesting part is how we going to calculate the index is how we're going to take the values. Right, so we're calculating, for example, do I have the not moving image? So this always corresponds to the center of the kernel, which means that okay, we can do this, right? So what we have, so this one, right? So this corresponds to this one, right? Okay, we can move it. Nice. And this is like this. And so we know that the kernel size is 1 by 1 or 3 by 3 in this case. Okay, so what we actually need to calculate, we need to calculate the start I and I, start j and j, right? So this is going to be the indexes for, it's going to be indexes for the slice, right? And that should be based on the size of the kernel. You know, there are some days when everything goes unexpectedly wrong and I have to finish the recording of the video much earlier than I expected, so as I need to go and I need to deal with something else. Maybe I will continue later today and I will record the continuation of this correlate2d video, or maybe I will have time only tomorrow, so let's see, or I will just finish the correlate2d valid implementation in between the videos and I will explain it in the next video. Sorry, but I mean, that happens. The main thing is to continue building things. But for now, thank you for watching and I see you tomorrow. Bye bye.